this question, is T an unbiased estimator for sigma squared, is equivalent to asking, is the expected value of this big expression out here, so is expected value of T of x1 through xn equal to sigma squared? Right, so this is what an unbiased estimator is. So what this is asking us to do is very simple. It's asking us to compute the expected value of this messy expression. Okay, so like I said last time, so there's nothing very scary about computing the expected values. So what you've got to do is compute expected values of each of these individual terms, and you basically have to use linearity of expectation, right? So this is the sum of a bunch of terms. So it is expected value of, let me write out the first step, which is x1 squared plus x2 squared, so xn squared by n, minus the expected value of x1 plus x2 plus xn by n whole square. Okay, so this is what we've got to compute. Okay. So what is this quantity, right? So now this one is something that is relatively easy because this is an average of n terms and we have the expected value of this. So if I know the expected value of each of these guys, then I can then use linearity of expectation, right? So let's call this term 1 and this term 2. Okay. So let's now first try to see how you would compute 1. And as I said just now, for computing 1, the key is what is expected value of xi squared for some I. Okay. So in general, if you have some random variable x, how do you find expected value of xi squared, right? So this is something which I will show just now, which is the and note that xi is drawn from this Gaussian random variable. So xi is a Gaussian random variable drawn from this Gaussian distribution with parameters mu and sigma squared. Okay, and we are asking what is expected value of xi squared. So observation, or you can think of it as a claim, is that this expected value is equal to mu squared plus sigma squared. Okay, and in fact there's a very sleek way of seeing why this is true, okay, which is that by definition of the variance which we saw over here, okay, sigma squared is equal to the expected value of, if I have a random variable x, okay, which is distributed as which is basically Gaussian, okay, with parameters mu and sigma squared, then the definition of sigma squared is expected value of x squared minus mu squared. Okay, and now xi is, I can use this by setting x equals xi for any I. Okay, and then if I just rearrange the terms, I get expected value of x squared equals sigma squared plus mu squared. Okay, so this is very simple, right? So this holds if x is a Gaussian. Okay, so computing 1 is actually very easy, right? So each of these is equal to sigma squared plus mu squared, and so 1 is the average of those. So 1 is equal to mu squared plus sigma squared. Okay. So now what we have to do is compute 2. Okay. And computing 2 turns out to be a bit more tricky, but it's still basically the same. Like I said last time, computing the expected value of anything is not a big deal. All you have to do is be brave and expand it out. So 2 is simply the expected value of x1 to xn by n whole squared, and this one is expected value of 1 by n squared times sum over I xi squared plus sum over I not equal to j for xi xj. This is exactly a calculation that we saw last time. Okay, and this one, so let's see how you would compute this quantity. So this term, this is exactly what we saw before. So this term, let me write out the answers and leave it for you to verify this online. So this term, there are n such terms, and expected value of xi squared for each one is like n times mu squared plus sigma squared. Okay, so each one has there are n such terms, so you have this n, and each xi squared has expected value equals mu squared plus sigma squared from what we saw earlier, right? So that's what we have. So that's why this term is equal to this. Okay, and now what is the expected value of xi xj when I not equal to j? Okay. So this is where we use this independence assumption. Okay, so xi and xj are independent random variables, therefore the expected value of the product is the product of the expectations. Okay, so this is equal to expected value of xi okay, and we know that each of these by definition is equal to mu. So each of these terms is equal to mu squared, right? And how many terms are here? So there are n times n minus 1 terms. Each one is equal to mu squared. Okay. So if you are not comfortable with this, try to see why there are exactly n times n minus 1 terms and convince yourself that there are exactly this number. Alright, so putting these things together, we have that 2 is equal to 1 by n squared times n mu squared plus sigma squared plus n times n minus 1 times mu squared. Okay. And so this one is equal to, so if I combine all the mu squares together and sigma squares together, I get 1 by n squared times n squared mu squared plus n sigma squared, okay, which is equal to mu squared plus sigma squared divided by n. Okay, so I have an expression for 2 and I have an expression for 1. Okay. And there's also a slightly more elegant way of seeing this, but let's not get into that. Okay. So I have an expression for 2, I have an expression for 1, and what I'm interested in is 1 minus 2. Right. So that's this term. Right. So this is the expected value of t. Putting these together, we get that expected value of t of x1, x2 to xn equals 1 minus 2, and this was mu squared plus sigma squared minus mu squared plus sigma squared by n. Okay. And this is something interesting. So the mu squared cancels out, okay, and this one is sigma squared times n minus 1 divided by n. Okay. So the expected value of this t, which was our guess for the variance, which was our guess for what sigma square should be, is not quite the variance sigma squared, but it's the variance squared times n minus 1 by n. Okay. So t is not an unbiased estimator for sigma squared. Okay. Not an unbiased estimator, because n minus 1 by n is not equal to 1, right? So if so, it would have been an unbiased estimator. But note that if n is large, this is actually pretty close to 1. Okay, so what we know is that this empirical variance, as I called it, right? So this is empirical variance is not quite an unbiased estimator for sigma squared, right? So it's off by this factor. Okay. So then the question is, how do you get an unbiased estimator? Using the samples x1 through xn. Okay. Now this calculation already gives you the answer, right? Because what it's telling you is that t was the expected value of t equals sigma squared times n minus 1 by n, right? So let's consider t prime xn, which is equal to n divided by n minus 1 times t of x1 through xn. So the expected value of t prime would be n by n minus 1 times the expected value of t by linearity of expectation. And we know that this is exactly equal to, so the expected value of t prime is exactly equal to n by n minus 1 times the expected value of t, which was, as we computed before, this was sigma squared times n minus 1 by n. So this is equal to sigma squared. Okay. So the moral of this is that this empirical variance is not quite an unbiased estimator of the variance sigma squared. Okay. But if you divide it by the number of samples divided by number of samples minus 1, then you get an unbiased estimator. Okay. And this quantity tends to 1 as n tends to infinity, but for small n, the difference is actually significant. Okay, so suppose I wanted to use 10 samples, then I have to divide the empirical variance by 10 by 10 minus 1, which is 10 by 9. Okay, it's almost like 10%. Okay, so it's the bias is actually significant when the number of samples is small. This is often called, this 10 by 9 is often called the correction term in the bias, and that is significant if the number of samples is small. N is small. Okay, and this tends to be a common theme. Like when you're trying to come up with unbiased estimators, it's usually easy to come up with unbiased estimators for large n, and for small n you have to add some bias correction terms.